Alright, so in this video we go over section 2.2, which is graphs of equations into variables, intercepts, and symmetry of graphs from equations. Okay, so graphing equations by plotting. So in this case, I don't want to spend too much time doing too many examples of this, because this is something we have been doing in a lot in previous courses. I will give you one example and to graph the equation y equals 2x plus 1. And in this case, you can choose as many points as you want. For example, for x equals, say, negative 2, 0, and 2. Maybe those 3 points are enough. So all we do here is make a little table and find y equals 2x plus 1. Okay, so 2 times plus 1, 2 times plus 1, 2 times plus 1. So 2 times negative 2, 2 times 0, 2 times 2. So let's simplify this. 2 times negative 4, that's 2 times negative 2 is negative 4 plus 1, which equals negative 3. 2 times 0 equals 0 plus 1, which equals 1, and 2 times 2, which equals 4, plus 1 equals 5. So we are going to get the following order pairs. In this case, we get the order pair negative 2, comma negative 3, the order pair 0, comma 1, and the order pair 2, comma 5. Okay, so let's plot these points and let's see what this is about. So we go to the point negative 1, negative 2, down to negative 3. We go 0, comma 1, and the point 2, comma 5. And in this case, if you connect these points, you should get a straight line. Okay, and you can just extend it. Of course, if you want to obtain more points, you might want to plug in negative 3 and positive 3. You don't have to. I think typically 3 points it's a good amount of points, but if you want to go all the way to 5, that's up to you. Alright, properties from graphs. So one of the most important aspects when it comes to graphs of equations is their intercepts. So in this case, an intercept is a point in which a graph either crosses or touches the coordinate axis, either the y-axis or the x-axis. Okay, so the point at which the graph crosses or touches the x-axis is called the x-intercept, and the point at which the graph crosses or touches the y-axis is it's a y-intercept. There was a little typo here. It's supposed to be y-intercept. Alright, let's find the intercepts given this graph. So x-intercepts. Those are going to be the points that either cross or touch the x-axis. And this is one, this is another one, and this is another one. Okay, so those are the points negative 3, 0, 3 halves, 0, and 4.5, 0. The y-intercepts, on the other hand, are going to be the points in which the graph will cross the y-axis. In this case, the point 0, negative 3.5, the point 0, negative 4/3, and the point 0, 3. Alright, so that's what we do when it comes to find the intercepts of a graph by looking at the graph. Again, just look at the points that either touch or cross the axis. In this case, the x-axis, the x-intercept, the y-axis, the y-intercepts. Now, what if we don't have the graph of a function and if we want to find the intercept from an equation? So we have a general procedure here to find the x-intercepts and the y-intercepts given an equation. So if you want to find the x-intercepts, set y equals to 0 and solve for x. Otherwise, in order to find the y-intercepts, leave x equals 0 and solve for y. Okay, so let's do an example. Let's do a quick example here. So we want to find the x-intercept. I'm going to call it x-int for short. X-int. So in this case, for the x-intercept, I'm going to set y equals 0. I'm going to set y equal to 0. Alright. And solve this baby equation for x. So I'm going to subtract 2 to both sides and divide both sides by 3 to get negative 2/3. So that's the x value. So this is not the final answer. Keep in mind that intercepts are meant to be represented as ordered pairs. Alright, so let's do the y-intercept. So for the y-intercept, in this case we are going to let x equal to 0 and solve to get y. So 3 times x, which is 0, that's going to give us 0 plus 2, which equals to 2. Okay, so the x-intercept will be the order pair negative 2/3, comma 0, and the y-intercept will be the order pair 0, comma 2. Where did we get this 0? Because we let x equal to 0. Where do we get that 0? Because we get the y equal to 0. Okay, let's do another example to find the intercepts. Alright, so we have 9x squared plus 16 equals 144. Alright, so let's find the x-intercepts. Okay, so to get the x-intercepts, we let y equals to 0 and we solve the equation for x. So in this case, 0 squared is going to be 0 times 16 is just going to be 0, so we are going to be left with 9x squared equals 144. And the next step is just to solve for x. Alright, so 144 divided by 9, we get 16. X squared equals to 16. And keep in mind that to get x by itself, take the square root on both sides. Don't forget the plus or minus here. Square root cancels with the square, and that's going to give us x equals plus or minus the square root of 16, which is plus or minus 4. So we are going to get to x-intercepts, to x-intercept of this form. So plus or minus 4, comma 0, which can be broken into 2. Negative 4, comma 0, and positive 4, comma 0. Okay. Now let's do the y-intercepts in the very same way. In the very same way, the y-intercept, for the y-intercept we set x equals the 0, and solve the equation for y in this case. Okay. So again, 0 squared is 0 times 9 is still 0. That's going to be 16 times 16x squared equals 144. Divide both sides by 16 to get x squared equals to 9. And take the square root on both sides. Don't forget plus minus for the right hand side. Keep in mind again, square cancels the radical. That's going to give us x equals plus minus the square root of 9, which is plus minus 3. Okay, so this is the solution to the equation. That's not the answer to the problem. So that means that we are going to have, by the way, I did a silly mistake here. This is supposed to be a y, not an x. Y and another y and y. Let me see if I can clean this up. Okay. It's y, not x, because it's our y-intercepts, not x-intercepts. So we are going to have plus minus 3, comma, what, never mind, nope, not this, 0, comma, plus minus 3. And from here, 0, negative 3 is 1, and 0, comma, 3 is the other one. So in this case, we are going to have a total of 4 intercepts, 2x intercepts, 2x intercepts, and 2 y intercepts. Just to look a little bit ahead of what we are doing. So this type of equation right here is the equation of an ellipse, which we are going to look at a later chapter. So let me show you how is that going to look like. 1, 2, 3, 4. Somewhere here, 1, 2, 3, 4, and 3 somewhere here. It's like a circle, not quite a circle. It's rather what we typically call an oval. But that's not how we call it. We call it an ellipse. But it's not important to know this. It's maybe you have seen it before. So but this is just a little look at the future in this class. All right. Now let's look at symmetry of graphs. Symmetry of graphs can be either symmetric with respect to the x-axis, the y-axis, the origin, or maybe not symmetric about any of these three. So here we are going to look at 3 pieces of information that we are going to use in order to determine whether some graph is symmetric about the x-axis, about the y-axis. Okay, so let's look at symmetry with respect to the x-axis. So a graph is symmetric with respect to the x-axis if for every point, it looks like I didn't add a negative sign here. There are a couple of negative signs missing here. So let's see, let's add them by hand. So is the point x comma negative y over here and negative x. Okay, so the PDF that you will be downloading is going to have this fixed. Okay, so in the video here there's a little typo, not on your paper. Okay, to get the symmetry with respect to the x-axis, we choose a point, and if we change the sign of the y-coordinate, and if that point happens to be on the graph of the of the given equation or function, well, on the given graph, then the function, the graph is symmetric about the x-axis. In a very similar way, a graph is symmetric with respect to the y-axis if for every point xy, the point negative x, right? In this case, we change the sign of the x value of the point, and it's still in the graph of that we have. Okay. The third symmetry, which is the symmetry with respect to the origin, if for every point, if we change the signs of both numbers, if it exists also in the graph, then the given graph is symmetric about the x-axis. So in this case, well, we have a lot of words, a lot of instructions here. Let's look at the examples to show you how it works. Alright, let's look at this graph and let's indicate whether they are symmetric about the x-axis, the y-axis, the origin, or neither. Okay, so let's see. The quick and dirty way to determine symmetry is, well, looking at the graph, and number one, you might want to consider the x-axis. In this case, I think it's kind of clear that the graph is symmetric about the x-axis, right? I mean, if you use the x-axis as a mirror, all right, think of it as a mirror. What's on the other side? It's reflected image, right? However, if we use the definition, okay, so this is what I'm going to do. I'm just going to take any point, preferably a point that it's easy to plot, like this point, which to me looks like the point 3, 4. Okay, so the point 3, 4. What happens if I change the sign of the y value, the point 3, negative 4? Now we need to determine whether this new point exists on the graph. So 1, 2, 3, negative 4. It turns out that it does exist. So this is evidence that the graph is symmetric with respect to the x-axis. Okay, what about symmetry about the y-axis? In this case, I'm going to change the sign of the x value, and I'm going to keep the same y value. Let's find out if this point exists. So in this case, 1, 2, 3, 4. Well, the point, it's outside of the graph, so that's why it's not symmetric about the y-axis. What about the origin? Okay, what about the origin? Let's see, let me use a different color. 3, 4. For symmetry about the origin, we change the sign of both numbers. Okay, so now I'm gonna go 1, 2, 3, negative 3, and negative 4, and it turns out a point that it's not in the graph of the one we have. So the only one that is correct is symmetric about the x-axis. All right. Okay, let's do another example. So we have another example, and in this case, if you use the quick and dirty way, you can see that the graph is symmetric about the y-axis, right? It is fine to just go with the symmetry like this, the short way. However, if you want to get very technical about it, if you want to use the definition, let's go ahead and do that. So in this case, I'm going to choose a point, this point right here, which is 2, 1, 2, 3, 4. And I'm going to apply the definition again. So 2 comma 4. Let me verify whether this graph is symmetric about the x-axis. To do that, again, change the sign to the y value, and let's see whether the point lies in the graph. Okay, so I'm gonna go 2 comma 1 2 3 negative 4. Look at this, the point, it's not on the graph, so it fails to be symmetric about the x-axis. What about the y-axis? To do that, change the sign of the value of x and determine whether the point exists. So I'm gonna go from the origin, -2 on the x-axis and 4, and look at that, the point lies on the graph of the function. So far the function is symmetric about the y-axis. Let's find out whether this is symmetric about the origin. To do that, change the sign of the point. Alright, and let's see. We go -2, -4, and we get somewhere where there's no graph. Okay, so it fails. So our conclusion is this is symmetric about the y-axis. Now in this case I chose the point 3 comma 4 and the point 2 comma 4 because they were easy to read, you know. However, you can do the test with your favorite point, preferably points that do not lie exactly in any of the y-axis or the x-axis. For example, I could have used the point 1 comma 3 and do the same. If you want to do that as an additional exercise, go ahead and try it. The point 1 comma 3 should work, or choose the 1 comma -3. It's fine. Over here I could have chosen the point 1 comma -2. It looks like, right, because there's a bunch of points here in the graph. However, not all of them lie exactly at a nice number, which by nice number we mean integers. Okay, so let's look at more examples of this. Okay, so let's determine whether this graph is symmetric about the x-axis or the y-axis. All right, so let's try the quick and dirty way first. Symmetry about the x-axis. Okay, this is a mirror, and this is the other side of the mirror. In this case, it's not symmetric about the x-axis because we don't see this graph on this side. And likewise, by just looking at the picture, it fails to be symmetric about the y-axis. Okay, let's do the test in the formal way. So I'm going to choose another point. All right, I'm going to choose a point. Let's see, a nice point. This one right here. The point 1 2 3 4 comma 1 2 3 4 5. So that's my test point. Alternatively, you can use the point 3 comma 3. That's another nice point. You could do it in whatever the point you want, or 1 comma 2. That's another one. All right, but I'm going to do 4 comma 5. Okay, symmetry about the x-axis. I'm going to change the value of the sign of the y value. Okay, and I will find out whether this point exists in the graph. So I'm going to go 1 2 3 4 5, 1 2 3 4, and then 1 2 3 4 5, -5. So this point does not lie in the graph, so it fails to be symmetric about the x-axis. Okay, maybe a sad face, why not? What about the y-axis? To check symmetry about the y-axis, change the sign of the x value of the chosen point. Oops, not 4, it's 5. This should read a 5. Let me erase this. Otherwise it's not gonna look nice. Alright. Okay, 4 comma 5. Negative 4 comma 5. So I'm gonna go 1, 2, 3, 4, negative 4, and 1, 2, 3, 4, 5. Alright, and if you notice, the point is it's in the middle of nowhere. So this is going to fail as well to be symmetric about the y-axis. Okay, let's do now symmetry about the origin. So I'm gonna go to the point 1, negative 4, then negative 1, negative 2, negative 3, negative 4, 2, 3, 4, 5, and oh, surprise! I mean, it doesn't look perfect in the graph. Oh, wait a minute. It was supposed to be here. And in this case, it works. It works. It is symmetric about the origin. Alright, what about this graph? This last graph? Well, clearly, I mean, the shape looks symmetric in a way. Okay, I will discuss that at the end. However, what I'm interested here is whether the graph is symmetric about the x-axis or the y-axis, and in this case it might be a little bit tricky to use the quick and dirty way. Alright, okay, because if you use the mirror right here, nothing is reflecting. The other mirror, nothing is reflecting either. So in this case, there will be no way around than choosing an arbitrary point. Okay, let's decide which point. Okay, this point looks nice. Alright, so in this case, the point is 1, 2, 3, 4, comma 2. So I'm gonna write that down, 4, comma 2, and I'm gonna check for symmetry about the x-axis. To do that, we change the sign of the y value of the point, and let's find out whether the point exists in the graph. Okay, so I'm gonna go 1, 2, 3, 4, and negative 2. The point is in the middle of nowhere, so it's not symmetric about the x-axis. However, let's find out how about the y-axis. Change the sign of the x value, and we're gonna have negative 1, negative 2, negative 3, negative 4, comma, positive 2. And in this case, the point is in the middle of nowhere, so it also fails to be symmetric about the y-axis. Alright, and then for the origin, change the sign of both. Negative 4, negative 2, and let's find out whether the point exists. So negative 1, negative 2, negative 3, negative 4, and then negative 2 is the point that I already did, and it's not in the graph of so there's no symmetry. So in this case, this is our conclusion. The graph is not, it is neither symmetric to any of the axes nor to the symmetric, actually this is symmetric about any of the axes, sorry about this rephrasing, any of the axes nor the origin. Okay, let me clear this out here so it doesn't look ugly. Alright. But in this case, well, looking at the shape, okay, this is like the vertex of this curve, right? If we trace an imaginary line here, it is symmetric. But in this case, it is symmetric at the vertical line x equals to 2. However, the point, the graph, not the point, is symmetric about the vertical line x equals to 2. Okay, so it's one of these tricky cases. So in this case, fails to be symmetric about any of the axes of either the y-axis or the x-axis, and also fails to be symmetric about the origin. Okay. All right. Other type of very classical questions. Well, you're given this sentence. So if a graph is symmetric with respect to the x-axis and the point 4, 2 is on the graph, name another point. Okay. The starting point is the given point 4, 2. Right? So what is another point? Another point okay, what do we do when we have symmetry with respect to the x-axis or about the x-axis? So in this case, change the sign of the y value, and that's the other point. Okay. In a matter of a graph, if I have a graph whose point is 4, 2, well then 4, -2 is symmetric about the x-axis, regardless of the shape of the graph. Okay, see how am I doing one graph like this? Another type of question. If a graph is symmetric with respect to the y-axis, is symmetric with respect to the y-axis, and here I need the word and. 6 is an x-intercept of the graph. Name another x-intercept. Alright, so what's the picture here if you want a picture? So, the graph has an intercept at 6 as an x-intercept. If the graph is symmetric about the y-axis, then this point will have its counterpart on the other side over here. Okay, so if you want to express this as an order pair, 6 as an order pair means the point P equals 6, 0. So another point, rather another x-intercept, will be this one right here, -6, 0. So this is all about symmetry when it comes to graphs. Now, can we find symmetry given an equation? Of course. So we are going to do exactly the same. So to check symmetry with respect to the x-axis, on the given equation, we are going to replace y by -y. To check symmetry with respect to the y-axis, we are going to replace x by -x. And with respect to the origin, we replace both x and y with negative x and negative y respectively. And the idea is to come up with the same equation whenever it applies. So let's look at a couple of examples here. Okay, let's see. So we are given three equations here, and they're asking us to determine whether the equations, the graphs of those equations are symmetric about the x-axis or to the y-axis. Alright, so this is what we are going to do. Okay, so for symmetry, about x-axis, we change the sign, replace y with negative y. Okay, negative y. So I'm going to write x squared minus the y will be replaced with negative y. Minus 4 equals the 0. Okay, so in this case we're going to use the smile rule, and we're going to get x squared plus y minus 4 equals the 0. Now you need to check this. Is this exactly the given equation? In this case it is not the same equation because we have a plus here, and the original equation, it has a minus for y. So in this case, no. Okay. Let's check for symmetry about the x-axis. The y-axis. To do that, we replace x with negative x on the other hand. Okay, so we do the changes in the x and not the y's. So minus y minus 4 equals 0. So we replace x with negative x here. And that's going to give us x squared, positive. Negative squared is going to give us positive. And in this case, look at this equation, compare it with the original one. And in this case is, yes, it is symmetric about the y-axis. Alright, now let's do the third kind of symmetry here, which in this case will be symmetry about the origin. So in this case we replace x with negative x, both of them, and y with negative y. So quantity squared minus quantity minus 4 equals the 0. So in this case x becomes negative x, y becomes negative y, both simultaneously. So we're going to get x squared plus y minus 4 equals the 0. And if you compare this equation with the original, it turns out that it is not symmetric about the origin. Let's do two more examples and we'll wrap up the section. Alright, so let's check symmetry about the x-axis. I'm just going to use sim with respect to x-axis for short. Alright, so we are going to replace y with negative y. So for x squared plus quantity squared equals 4, where the quantity squared is the negative y squared. So that's going to give us 4x squared plus negative quantity squared. It's going to give us also positive y squared equals 4. Compare the equation that I've just boxed with the original one, and in this case we obtain the exact same equation as the original. So yes, it is symmetric about the x-axis. Let's do another one. Symmetry with respect to the y-axis. For this we replace x with negative x. How about we highlight this? That's the important operation here, to replace the x with negative x. So 4 times quantity squared plus y squared negative x. So negative x quantity squared, in this case, is going to give us again 4x squared plus y squared equals to 4. And in this case, again, if we compare, we get the exact same equation as the one that we are given. So also yes to symmetry with respect to the y-axis. Now let's find out what about symmetry with respect to the origin. With respect to the origin. And in this case we are going to replace x with negative x and y with negative y. We change both of them. Alright. 4 times quantity plus quantity squared. So negative x squared, negative y squared. So we're going to get 4x squared again plus y squared equals to 4. Alright? And again, compare this final equation with the original one. So this is also a yes. So in this case, the graph of the equation 4x squared plus y squared equals to 4 is symmetric about the x-axis, the y-axis, and the origin. And again, if you recognize this form, not that you are expected to know this, again, this is an ellipse. This is an ellipse which looks like, I think it's going to look like, divide both sides by 4. It's going to look like this. And notice the symmetry about the x-axis, the y-axis, and the origin. But you're not expected to know this at this point. We're going to learn, we're going to revisit this way later in the semester. Okay, so let's look at one more example and we call it a day. So, x to the 4 plus 1 divided by 2x to the 5th. So symmetry with respect to the x-axis, that's going to be so in this case, y becomes negative y. That's what we do to check whether the equation, the given equation, is symmetric about the x-axis. So I'm going to replace this y with negative y and everything else remains the same. Now I'm going to isolate the y by multiplying both sides by -1. So that's going to be y equals the negative. I'm just going to put it in the very front. Now let me box this equation here. Compare with the original one. Is it exactly the same as the original one? In this case, it is not. So it is not symmetric about the x-axis. What about the y-axis? To do that, replace x with -x. Alright, respect x with -x. And so y equals something to the 4 plus 1 divided by 2 times something to the 5th. Okay, so replace x with -x and simplify. So x to the negative x to the 4th power. That's going to leave me with positive x to the 4th, because this is a negative being raised to an even power. That becomes a positive. And negative raised to an odd power, that's going to give me 2x to the 5th, but negative. In this case, well, this negative could be either in the front or right here. Now let's see. Let's compare with the original equation, and in this case it is not the same equation, so it is not symmetric about the y-axis. Finally, let's check symmetry with respect to the origin. So we replace x with -x and y with negative y. Okay, so y becomes negative y, and x becomes -x. Oh, this is not squared, by the way. This is to the 5th power. Let me clear this so it doesn't look messy. Okay, to the 5th power. Alright, so we're gonna have negative y equals x to the 4th plus 1 and negative 2x to the 5th. So there is something very interesting that is going to happen here. So in this case, I'm going to multiply both sides by -1, and negative times a negative becomes positive. This negative times this -1 become positive. And in this case, it's kind of funny how a graph is neither symmetric about the x-axis nor the y-axis, but it is symmetric with respect to the origin, because we get the exact same equation here. Alright, so this is the end of this section. Okay, so I'll see you on the next video.